So first, hi everyone. My name is Diji from UC Santa Cruz, and today I'm gonna present our work called MRAG, Multi-Round Retrieval-Augmented Generation through Learning Inner Monologues. So this work is led by UCSC, but we got lots of support from many good researchers across different institutions, so many thanks to them. And there are two keywords I would like to highlight before I start is multi-round retrieval and the learning inner monologue. So let me get started. So first, a little bit about the background. We saw that LM show great potential on the ability beyond the language, such as reasoning. But meanwhile, they suffer from two well-known problems, hallucination and the static knowledge-based problem. So with knowing those two limitations, many researchers right now believe that RAG can provide some help. And the key of RAG is to solve the problem on the based on the retrieved document. And from the implementation side, there are two very popular approaches to empowering model with the retrieval ability. Those approaches are good, but unfortunately, both of them have some clear limitations. So first one is called joint training. So this approach jointly trains the LLM and the retriever in an end-to-end manner. So the performance of this system is usually good, but this is very expensive approach because if we want to update something, we have to retrain or fine-tune both embedding model, the index, change the index, and also train the LM, the whole system. And besides, this kind of solution act like a black box, so it's lack of interpretability. And another approach is, I call it a separate training here, but by the way, I saw some of you attended my two learning tutorial yesterday, so you probably know I also call this as a LM-centric or LM2 work. They are referring to the same thing. We consider the LM as a tool, and we consider the search engine as a tool, and we do not touch it during the training stage. And this paradigm consider the LM and the retriever as two totally separate model, and they connected through API calls. So the good thing is that we can improve each part individually, and the interpretability is much more better than the previous one because once system goes wrong, we can open this box and check if the problem from retriever or the large language model. But the downside is that this result is usually suboptimal. The performance of this system is usually suboptimal comparing with the previous joint training works, because both module components are not optimized based on each other's capability. So those existing works from those two categories kind of motivate our technical goal. We want to build a system to combine the advantage of those two different RAG paradigms. And besides the technical background, I would like also to share one use case, actual use case example to show the more motivation of our work and also showcase what our system can do. So this is actually a real question I got months ago. My friend recommended 2 hotels for my SIGIR trip, and he told me that the first one is closer, but the second one is much more cheaper. So which one should I pick? I cannot make the decision directly because I need to do some reasoning and do some search. So the first sub-question came to me is, what are their prices? So to answer this, I have to do some search. I use a Google search engine. So the result shows the first one is more expensive for like $50, and the second one is truly cheaper. And now I got enough information for those hotels, but I still need some information from my side to make the final decision. So luckily, I recall that I actually have some funding for this trip. I mean, thanks to SIGIR. So I kind of ask myself, can my budget cover this? Then I do a search within my memory, and I realize, okay, both are within my budget. So this decision now can be easily made. So from this example, as you can see, to answer the real-world question, we, as a human intelligence, we might prefer to do the multi-round thinking and use the IR engine when needed. So for those two self-asking sub-questions shown in the middle, even I didn't speak it out during my thinking, but they all contribute to my final reasoning chain within my mind. So this reasoning skill is known as inner monologue in cognitive science, or some researchers call it inner speech. They are the same thing. And it is defined as a stream of thoughts, feelings, and inner conversations that occur within person's mind. So this brings more motivation to us. We want to build a system that first can handle the real-world problem, like the previous example, and more importantly, we want to teach the model with the inner monologue ability, and also with the help, seek for the help from the search engine when needed. And here is how we define those concepts. We format the inner monologue as a conversation among those three components. The first we call the LM as a reasoner, which acts like a human brain. And we use a retriever for information collection. And the last part, we have a re-ranker, or we call it a refiner, to improve the retrieved result. And now let's dive into the actual system design. So we use a predefined search engine as a retriever, and the LM as a reasoner. Both them are fixed. We do not train them at all during the whole training stage. So we just train 3 LoRa's for 3 different abilities. And in case you are not very familiar with LoRa, LoRa can be considered as an actual adapter layer outside of the LM, as shown in the orange blocks in this figure. So it can be connected to the LM for a specific application, and it also can be disconnected from LM with nothing hurt on LM's original capability. So we train 3 LoRa. The first one is we call it refiner, or is a re-ranker. We use that to re-rank the retrieved result to improve the recall at 5 performance. And then we train the questioner LoRa that will be used to help the reasoner to propose a good query to the retriever. Finally, we train an answerer to answer the question after all the required information has been collected. So the overall system looks like this figure. So first, the questioner, the question from user goes into the reasoner, and the reasoner uses a questioner LoRa to send a query to the retriever. Then we use a refiner LoRa to re-rank the document and send them back to the reasoner. Finally, reasoner can choose to ask more questions or providing the final answer based on the current information, and you use this answerer LoRa. So after seeing our conceptual design, here is how we actually implement our system. First, we pick the models. We use a fast search engine. We use a fast Facebook AI similarity search as a retriever, and use a semantic transformer as an embedding model. So actually, this could be many other search engines, including like API or some traditional like BM25 search engine. That will be all work. And for the LM, we use a Llama 2-based large language model. And also for the training algorithm, I want to mention is we use a PPO as a training algorithm. So little bit background on that. So PPO is a policy-based reinforcement learning algorithm. And in our case, we consider the LM as a policy network. So the action space will be the dictionary of the large language model. And the action is a generated token. So as long as we can get somehow get the reward signal from the environment, we can use the PPO algorithm to optimize the policy network. In this case, should be the LM. Or the LoRa adapter. So as I mentioned, we have the questioner and the answerer training. So the first stage, we train the questioner. As mentioned, after the task or the question goes into the reasoner, it could use a questioner LoRa to propose a query to the search engine. So after the query brings some document back, we can optimize the LM based on the environment feedback. In our case, we designed a progress tracker with a reward function to provide this feedback based on 2 signals. One is overall retrieval quality, and another is a final answer accuracy. Here's our reward function. It mainly has 3 parts. The first one is overall retrieval quality. So the I here indicates the current turn, and the D sub I is distance from the retrieved result to the gold passage. So this requires the dataset to provide a gold supporting passage label. Actually, this is one limitation of our work. And we also have a discount factor to encourage questioner to ask fewer questions. So this is about the retrieval quality. And we also have a final prediction accuracy. So this is simply a F1 score, that F1 score between a predicted answer and the ground truth answer. Finally, we have a KL penalty between the current updated model M and its starting point M0. And this is a standard factor in RL since we kind of want to make sure the updated model won't be diverged too far from the starting point. So this concludes our reward function, and using this reward function, we can use some score to help with PPO training. Remember that we have a questioner LoRa and also an answer LoRa. So this is because we claim that proposing a good question requires different ability versus answer the question based on current information. So we design those 2 LoRa for different tasks. So after the questioner is well trained, we need another training stage for this answerer. The input should be the original task content, the queries, and all the retrieved documents. And we expect the model to output the final prediction. And now the task is pretty simple and straightforward. This is a typical supervised fine-tuning setting, and the training is not that hard. It's just a standard next token prediction training. So we test our system on hop QA, which is a famous multi-hop question, multi-hop knowledge-based question answering dataset. And this dataset, question from this dataset always requires system to retrieve multiple documents from the Wikipedia corpus to answer the question. And the result shows that IMRAG outperform all existing LM-centric work and the joint training works. So let me now conclude our work. The first thing is inner monologue-based RAG, or we call it IMRAG, combines the advantage of 2 different RAG paradigms. And as a LM-centric work, it has flexibility and interpretability. And also, IMRAG has a system-level end-to-end optimization, which results in a very good performance. And we also want to highlight that this work simulating the human inner monologue process while doing the multi-round retrieval. So IMRAG, kind of this approach was born for complex task solving and multi-hop reasoning. Besides, this is kind of important, we consider inner monologue is a reasoning skill, which is not about the domain knowledge. That means we do not expect any domain-specific relearn or retrain for both human and machine when we come to an unseen new domain. And one final thing, this paper is just the first step toward our goal, which is learning how to do the inner monologue between LM and the retriever. So many further improvements can be done. And if you are interested in our work and this direction, please always feel free to reach out to us for more discussion. That's all my slides, and I'm open to any questions.